consecutive to that is IIT Delhi. The participants from IIT Delhi are Tejas Anand, Salil Gokhale, Mihir and Dhruv Ahlawat. The next team, which is sitting right at the left is IIT Kanpur. And the participants from IIT Kanpur are Dinesh R, Viral, Maharajan and Shruti Subramanyam. We welcome every one of you and wish you very good luck for the upcoming quizzing rounds. Now I would like to introduce our esteemed judges. Our judges for this round, that's physics deep thought, are Professor Emeritus Deepak Dhar and Dr. Ashish Arora. Dr. Arora is an experimental physicist investigating magneto-optic effect in semiconductor system. He was recently awarded the Young Achiever Award at DAE Solid State Physics Symposium. Professor Dhar is a distinguished theoretical physicist awarded the Boltzmann Medal by International Union of Pure and Applied Physics Commission on Statistical Physics. Among his many contributions to statistical mechanics, the exact solution to the sandpile model and the concept of spectral dimension of fractal are two most renowned. Both the judges were there during the framing of the questions. They helped our question making team. They are also here now for the judging. I thank them for being present every time. Now for the judges and the audience and also for the participants, I would like to briefly go through the rules for this brief thought. So the time for brief thought will be 2 hours per subject. There are 4 questions. One question will around take half an hour. So for the marks, there will be 20 marks per question. There will be one directed team which will choose the question. The directed team can get maximum, if they answer correctly, maximum of 20 marks. Then there will be the passing on of the question in the pre-decided order. In this order they are sitting. If the directed team is, for example, team A, then the team B, which is sitting next to the team A, will be, the question will be passed on to the team B. They will have a particular time and they can represent, and similarly the passing off of the question will be there. Now for the marks, maximum marks that can be awarded to the directed team is 20. Maximum marks that can be awarded to the first passed on team is 10 marks. The maximum marks that can be awarded to any other team who will give the correct explanation is 5 marks. Now about the time. In initial 3 + 1 minute, that's kind of flexible. There will be the podium coordinator will present the question. The presentation of question will be there. Once the presentation is finished, then the directed team, whichever is the directed team, have the chance to clarify their doubt regarding the question. So they can ask the doubt from the question making team in that 1 minute. Immediately after the doubt of the directed team is clear, the timer of 15 minutes will start. This 15 minutes of time will be for the first team. For first team have to think and present in that time. It's on them. Whenever they want to present, they can. So after this 15 minutes is over, immediately after the 15 minutes, without a single second lag, the question will be passed on to the next team, and they will get 2 minutes to present. They won't be getting any extra time of thinking because they already had 15 minutes. After that, after the second team time of 2 minutes is over, then consecutive team get 1 and 1 minute. And in this 19 minutes, the presentation of every single team will be done. After this, there will be judges time, that's judges clarification time. They can ask their doubt with any of the team. They can clarify anything they want to. After the judges clarification is done, this question is done, then our QMC or any member of the question making team will come on the board and will explain the answer to the audience and to the participant. After this, the first question ends. Similarly, the another question will be there. Now, two things. The decision of the judges will be final. There won't be any debate on that. We have thoroughly go through the question, and we are like they are correct. So there won't be any further thing. One important thing: if any of the initially the clarification time is only for the directed team. If any other team or any team have any doubt, in between those 15 minutes, they can just raise their hand. One of the QMC will come and will tell you regarding your doubt. That's all. We will be punctual about time and everything. Now I welcome Moksh and Vignesh, who are the podium coordinator for today's deep thought, that's of physics. I will hand over the mic to them.
Okay, good afternoon finalists. Welcome to Physics Deep Thought. I am Moksh Kothari.
And I'm Vignesh Lakdwan.
And we'll be your podium coordinators for today. I request the judges to pick out a chit to select the first team. Okay, so IISER Bangalore will be answering the first question. After that, IIT Bombay, then Delhi, then Kanpur. Okay? So you can choose your question. Your questions are Gibbs,
Yes, Papa.
eating camphor,
No, Papa.
disco femto,
None, Papa.
chem major, ha ha ha. You can choose your question.
Gibbs, yes, Papa.
Okay. Anagha measures the Gibbs potential G of a fluid as a function of the molar volume V at different temperatures T1 less than T2 less than T3 less than T4. Upon plotting G against V, she obtains the isotherms shown in the figure 1a. Assume Gibbs potential curve as being the potential curve of the system. You can see the figures here. Your first question is, explain what is physically happening in the system as we increase the temperature. In particular, explain the significance of the equal minima obtained at temperature T3. Your second question is, figure 1b shows the Gibbs potential versus molar volume curve for the same system at a different temperature. The different curves once again represent isotherms at increasing temperature. Explain what is happening to the system as we increase the temperature based on the given plot. She now defines a pair correlation function, G of R, as the ratio of average number density of particles in a shell of radius r centered at an arbitrary particle to the number density of ideal gas at distance r. You can see the expression for G of R. The particles of the substance interact with each other through a Lennard-Jones potential shown in figure 2. Your third and final question is, draw the plot of the pair correlation function to R for system at T1 and T4 and explain qualitatively how they differ from each other and why. Best of luck. Do you have any questions, any clarifications? Okay. If you have no clarifications, then your time starts now. I see Bangalore has a doubt. Can the QMC come in?
Yeah, so
You have 5 minutes remaining.
So basically, the first diagram, it represents the Gibbs potential of a fluid in different temperatures. So yeah, so this is the temperature T3 represents a phase transition, and so when it was in T1, so this was T1. The Gibbs potential for this lower volume phase is lower. So the phase will be in this. So this will be the predominant phase. But as you increase the temperature, this minima rises, and they become equal. So both phases have equal probability now, and now the phase transition starts. So, and here you see that this phase becomes more predominant. So this has more specific volume, and it is more predominant at a higher temperature. Now,
now for the B part, basically we see that given the first part, all of the it's in the phase transition for all the temperatures. So basically, from the first part itself, since we know for a real gas, relating from that, we have real gas equation which is cubic in V, and we get curves like these, and then depending on situation we either get one solution, three solution, degenerate solutions. So it's similar situation to this. Now this is the critical case where for all temperatures we get phase transition in, so basically we get degenerate solutions in each of the case.
So so draw the phase diagram. Phase for this.
This one.
So this is the phase diagram where suppose there is no phase transition between the gas and the gas and the liquid. So at all temperatures.
So generally we remember take this region as almost constant one, because the upper region and the lower region have equal area. So we think that this corresponds to something of this sort of characteristic, but for the fluid. Now,
You have 2 minutes remaining.
So for the GR case, we see that for a gas. So initially, when R is small, we know that for a gas the particles are far away. So when R is small, the GR will be small, and as you increase the R, it'll saturate. This is for an ideal for the ideal gas scenario.
it's fluid. fluid only. It's fluid only, but like we are thinking in terms of gaseous because
The
are
higher,
higher density.
the higher,
Yeah.
the
So the particles won't be close enough because of we know the Leonard potential is like this. So there is high repulsion. So the particles don't want to be close to each other. So the G of R is close to 0 for lower R's, but it after large distances, it's almost to the it's almost 0. So it saturates to a constant level. Now for the two potentials, one case it's for a lower molar volume, while the other case is for a higher molar volume. So the lower molar
30 seconds.
volume, the particles will be closer to each other because like this peak is flattened. So the repulsion force are lesser in this phase as compared to this phase. So
the GR will be much steeper. So we think it will be much steeper and it will reach saturation much at a much lower rate.
one is, but the saturation of both will be at the same level because they are density upon density. So it eventually reaches
Your
one.
time is up now.
Yeah.
I request you to get back to your seat. IIT Bombay, you can start presenting. Your time starts now.
So as we know that a lower Gibbs potential means more stability. So over here we can see that this is a phase transition. We go from a liquid fluid to a gaseous fluid as we increase the molar volume. At lower temperatures the liquid phase is more stable, and at higher temperatures the gaseous phase is more stable. This is a state transition graph. In A part we are going from a liquid to gas. As molar volume increases, molar volume is directly proportional to the temperature upon pressure, and this is our temperature and this is the pressure. So we are going along this path from a liquid to a gaseous state. In the second diagram, it is
1 minute.
In the second diagram, it can be seen that both the minima are at the equal level in all cases, which means that as we are traversing along the state transition of the liquid and gas. So our temperature is increasing, and we are at an equilibrium of liquid and gas at all temperatures. For this second part.
30 seconds.
Okay, so for the second part, we feel we just write the expression for the density at a general point Rn divided by the total density. So on integrating the expression, like we knew the total density, total number of particles is n. So on solving, we get like we didn't arrive at the equation, but this was the method that we followed for it.
Okay, IIT Bombay, your time is up. IIT Delhi, you can start presenting. Your
so
time
as a-
starts now.
So as the previous teams mentioned, in the first part, we have phase transition, and at T3, we have the transition point temperature. And because at the minima, that's the particular state we're in. And in the second part, as the temperature increases, we approach the critical temperature and the triple point, as these guys mentioned, where all the states exist in equilibrium. And after T-4, there is only one state, regardless of pressure and volume.
In part 3, as we can observe here, the temperatures are increasing from T1 to T4. So at T1, we expect the particles to be more closely packed than at T4. And since R min is the distance of equilibrium, we expect the maximum G of R value to be at R min. So the graph of T1 should be like this, graph of T4 should be like this, and both should approach 1 as R tends to infinity, because that's the ideal density that we are looking for. So that must be 1, the ratio.
Okay, your time is up. IIT Kanpur, you can start presenting. Your time starts now.
Okay, for the first part, both the minimas they represent the states. So for T1, the liquid state dominates. For T2 as well, it dominates. Whereas at T3, it represents the state transition. T4, the gas state dominates. And the Gibbs plot of T4 is more than T3 is more than T2, because more the temperature, lesser the stability. So that was for the first part. Now for the second part.
So for the second part, what we summarized was that so you're moving along the coexistence curve, as in where your phases actually like coexist, and as the temperature increases, they basically blend into one single phase. At T4 dash, it's basically indistinguishable.
So basically for part 3, initially as R goes to 0, they repel each other with very high forces, so therefore it will be close to 0. As R goes to infinity, be closer to the ideal gas, and then at R min we'll be having the maximum density because that is the lowest point of the potential. So
Kanpur, your
now as
time
the
is up
temperature
now.
changes,
Kanpur, your time is up. Okay. I request the judges if you have any questions for the finalists.
Let me start with the IISc. You said that in the there is a transition in one case, but in the second case it's always a phase transition. What does that mean?
So we think it's a supercritical phase, and both the phases coexist together. And there is no clear phase transition between a discontinuity in the derivative of G while phase transition is happening. We just think it's a phase where both the things can coexist together.
I thought you said that at low temperature it is this lower minima, at high temperature is the other minima, then there is a jump from one minima to another. So phase transition occurs at that point or everywhere?
No, we think so. Like since both of the phases are at like equal level of minima, so both of them both of them exist in equilibrium, and so it's the case of supercritical fluid where the fluid phase and gaseous phase coexist, and we cannot differentiate between them, so it's behaving like a gas, but it has a higher density, so it's also like a fluid. So it's something like of that sort.
Okay, not fully clear to me, but let us move on to the second one. So you said there is this formula for G of R written above, where there is a capital R. What is that? Huh?
And we are taking a shell at small radius, like small r.
So big R is the size of the
Bigger sphere.
So this G of R can be pretty big, no? 4 pi big R cubed by 3.
Yeah, but there should be some constants also, which we didn't integrate it properly. But this should be proportionality to this.
Just from naive arguments, it follows that G of R must go to a finite constant value and not increase very much. Okay,
Yeah.
so anyway. Sorry. Okay, in your picture it is not shown. Okay, anyway, I think that is all the questions I had. No question for the 14.
Okay, now I request the question maker Dhruv to present the solution.
So in the first part, you see that the system settles down, equilibrates at the global minimum, and this is T1. Now at T2 also it settles down to the global minimum. At T3 you have both equal minimas, so it's like the system is at the coexistence curve, and once you go from go above T3, the T4 temperature, you see a sudden density shift. So what has happened is a phase transition. So if you draw the PT diagram of the system, it's somewhat like you are going from here, T1, and this is like the T3 where you are at the coexistence curve. Both the phases coexist, and here somewhere is T4. In the second part where you have equal minimas for T1 prime, T2 prime, and that is the phase where you are moving along the coexistence curve. So T1 prime may be somewhere over here, T2 prime may be somewhere over here, and at T3 prime, where you see the broadening of the Gibbs potential, it represents absence of any restoring force, so you see fluctuations in the density. That's the phase where you are at the critical temperature. You no longer can bifurcate, like differentiate between two phases. And when you just see one minima, you have crossed the critical temperature. That's the T4 prime curve. Okay. Now when you are in the third part, when you are drawing GR curve versus R, for the first few R prime or R naught, the GR value stays to 0 because it represents the radius of the arbitrary particle that you are choosing. So nothing can cross that radius. After that, you see a sudden peak. That is because it's interacting through a Lennard-Jones potential. So you have this, you have that attraction of the particle. So it's like a arrangement of layer around that arbitrary particle. But after that first layer, you have another layer which wants to come near, but it is facing the repulsion from that second layer as well. So there will be a dip from the ratio, and you will, and this thing repeats for multiple times, and at large distances the diffusion dominates, and then you see this asymptotically going to 1. Now this is for, let's say, liquid state. Then what you will observe for the gaseous state is that you have less density, so the particles are for, like, you will till R naught you still see the 0 value of GR, but after that you will see that the peak is not so strong because the density, because the number density is less, as it's a gaseous state and the density of particles is low. And now since the density is less, the particles have more freedom to move around, and so you will see a shift in this peak. The peak will be there, which will be of lower amplitude, but will be shifted slightly rightwards. And the same things go on, and it again goes to 1 asymptotically. So that's the point.
So IIT Bombay, you get to choose the next question. Your options are question number 2, 3, and 4. Third. Arpita, a curious first year, is goofing around with the Young's double slit apparatus as shown in figure 1. Out of curiosity, she removes the pinhole in front of the first hot filament bulb. To her surprise, she sees no interference pattern and only 2 bright spots of white light in front of the slit. Your questions are, first, explain how removing the pinhole destroys the interference pattern. The second question, Arpita now places the filament bulb far away from the screen. Describe the image on the screen and give a mechanism for its formation. Still unsatisfied, she procures a high-speed light detector and measures the intensity of light at 2 different points on the screen. She then plots the intensity tying graphs for these points in the same figure, starting at the same instant in time. The measurement runs for a few time periods of the peak frequency of the filament bulb and is repeated for both cases. Your third question, qualitatively sketch the plots that Arpita will observe and explain their features. The assumptions in the question are, the hot filament bulb can be modeled as a closed packed set of independent sources with random frequency and random phase that can fluctuate with time. The second assumption is the high-speed photodetector can measure the intensity of light with infinite precision in time. Do you have any doubts?
In the first case, removing the pinhole means removing that entire screen, or does it mean opening that pinhole? So the entire screen is removed. Okay. Okay.
Your time starts now. Good luck.
दे कि sources coherent नहीं होंगे हर जगह.
So in the first question, because the pinhole is removed, both both the slits, we have non-coherent light rays coming from the light source. So this will not cause any constructive interference. It will just basically all the rays have random frequency and phase. So it will basically just converge on these 2 points here. Yeah, because the rays are coming parallel to these slits, it will just cause some bright spots at these 2 points, and there will be no slit formation in the standard YDSE. Okay. And in the second question, when we are placing it far away, the rays are now parallel to the slits, and again they still form the same image. This will actually be formed because of the diffraction happening at these two slits, and those 2 diffractions will cause constructive interference on these and destructive on others. So it will be the intensity will be less other than these 2 points.
So like exactly for the image, we like each of the slit produces a diffraction pattern, and the resultant intensity shall be the multiplication of intensity due to diffraction and the one due to YDSC. So like the resultant intensity formula is something like this on the screen for the second part. We have not done it.
Third part source.
So can you actually plot the function? What it looks like? Oh, they are trying.
You have 7 minutes left. You have 5 minutes remaining. IIT Bombay, you have 2 minutes remaining.
Okay, so for the third question, since we have a high-speed lie detector, we can measure the intensity at a particular point of time. So when we're looking at a particular point of time t equal to t naught, it will the intensity graph will look like YDSE because the light ray is emitted of a single particular frequency and phase. So that will be coherent for both the slits. But when we consider the time averaged over a small interval, this will average out and form an envelope of diffraction. So intensity will look like diffraction between the diffraction over the two slits.
So the envelope, the waveform which is inside is that of a YDSE, and on an average it is that of a diffraction pattern. That is how the waveform will look.
You have 1 minute remaining.
And since in the last part the phase is randomly changing, so intensity will change accordingly as the phase changes. If we consider intensity as a function of phase and time, the final graph will look something like this.
We can assume it to be a random like sinusoid in bit like restricted between 0 to 2, and the exact pattern will be depending on the time. So it would be a random cosine function.
IIT Delhi, your time starts now.
In the first part, when the pinhole is there, it acts as a coherent light source, and you can see the YDSC pattern. But when you remove the pinhole, the bulb is an incoherent light source. So it will just form a pattern similar to the drop in intensity due to inverse square law. So there will be two bright spots right in front of the two holes, and at all the other places it will reduce the intensity because it is at a further apart distance than those 2 points.
For the second part, when the bulb is far away, the light that will come to both the slits will be parallel, and we can assume that diffraction will happen in both the slits. And during diffraction, there will be interference pattern observed. But since there are random phase and random frequencies that we have in our condition, both the diffraction patterns will roughly overlap to produce a pattern like this with a maxima at the center, and as you go farther out, it will be lesser and lesser. And since again, for the third part, because we have random frequency, random phase, and independent sources, what we think that will happen is that with time, what we see will roughly remain the same. But since we have infinite precision photodetector, we can imagine something like random intensity happening, but all around a certain, like at a particular point, there will be a random intensity with certain times due to interference. But with the naked eye, we can probably just see only a specific intensity at one point.
IIT Delhi, your time is up. IIT Kanpur, your time starts now.
Okay, for the first part, when the pinhole is there, we can get coherent sources of light at A and B, and the normal YDSC pattern is observed. And when we remove the pinhole, the sources are no longer coherent, so we do not observe any interference. We get the normal, say, diffraction pattern, in which we get two bright spots with decreasing intensity as we go in either direction. Okay. So now next thing is when the bulb is far away, we get plain random waves, so we get coherence again. So in this case, what happens is we get again a YDAC pattern, YDAC kind of pattern, but there are different frequencies involved. So the central maxima will be there, the first maxima, second maxima will be different. So last part is about the graph. So about the graph, you see at the central maximum, that is at 0, we'll have an intensity of 4i.
IIT Kanpur, your time is up.
So basically in the first part, when pinhole is there, the light sources are coherent. Like source at that point is coherent. But when we removed, we lost the coherency. But now when we move the source far away, since the location is far away, when incoherent sources are at a distance, when they reach far distances, they receive some coherency. We can observe this because we use sunlight for doing YDC experiment, but the sources in sun are like incoherent, but at distances they become coherent. So we get the but they are still made of many colors. So we get overlap of all the colors. So we get the some exponential kind of decay. And for the last part, we can observe the plots for different points. If we take the Fourier transform, like if we write the function of the.
I see your time is over. Please return to your seats. Now to the judges, do you have any questions for clarification?
Okay, let me start with IIT B now. So you said that if you have a single slit, then it becomes coherent. Why is that?
We said that if we don't remove the screen, then it will be coherent.
Yeah, so if you don't remove the screen, why does it become coherent?
If we don't remove that whole pinhole screen, it is just one single, only one single frequency will be passing at a time.
One single frequency, but white light was being sent, no?
Like the diffraction happening at the pinhole. So that light will be passing through the slits, and hence we get the pattern on the screen when pinhole was there.
So,
but once we remove the pinhole.
And what is this B you have written in that formula, and phi?
Beta is just a factor of pi into phase by lambda, where phi is again some function of path difference, like how far we are seeing the pattern, like from the origin, center of the screen.
Is it related to the position along the screen?
Yeah, so like the beta and phi are the same, I just used the different symbols.
Okay, all right.
So when there is a pinhole, then you said that, okay, something becomes coherent. But when you remove the pinhole, just from the bulb, things are incoherent. I could not follow that. Can you explain that a bit again? Because you said that it's one single frequency passing through the hole, because bulb is a white light source. Even if you have a small hole or large hole or whatever, it will be all frequencies going through. So can we consider coherence as some phenomena related to single frequency, or what is it?
Sir, we were saying that when we are removing the pinhole, both of the slits will have some light which will be incoherent.
Why?
Because let's say there is no pinhole, there is just one bulb, and it has random frequencies and random phases which are fluctuating with time. So at each point of time, if the bulb is not placed far away from the screen, we can't assume that they are parallel. The light beams that are coming are parallel. If let's just assume that the bulb is placed a little near to the screen, so that we can't assume that the light they are parallel. And so we can't say that both of them will have the same, like both of them can't interfere exactly.
Yeah, I'm not sure what is parallel or not parallel, because we have to talk in terms of probably waves and not rays, which you have been talking all the time. So I was not convinced. Anyway, so we can move on to IIT Delhi.
So just can you explain the third part a bit better? I didn't follow exactly what was said.
So the term of beta is due to the path difference of the two light waves that are arriving, and the cos square omega t factor is due to the phase difference. Because the light is not monochromatic, it's consisting of different frequencies. So if we add up all those expressions, we will get a uniform intensity, like the curve I've drawn on the right.
So this cos squared omega t is it's changing at the frequency of light?
It's changing with time. For a particular frequency, that is the expression. Because there are multiple frequencies, we have to add all of them up. So that would, because we can write cos squared omega t as 1 plus
so
cos.
I was asking about the third question, about this qualitatively plot of the measurements at different points on the screen.
Okay, at different points.
Third question, when she takes this high speed detector, what will she see?
Oh, okay. So it would be a curve of sine square beta upon beta, and beta would be changing with the screen.
Okay, all right. Okay. I think I will let it be. Okay.
Yeah.
Okay, thank you.
Now to the QMC to present the solution. I need chalk.
Cool. So for the first part, to explain how the pinhole preserves an intensity pattern, if we have the source here, the source radiates light that is both temporally and spatially incoherent because it's a black body. The emission process is random, right? So what that means is light at this point and this point from the source is not correlated. However, if you put a pinhole, all the light falling on the pinhole is close enough to be spatially correlated. And what that implies is that this pinhole can now behave as a coherent source of light. And if we have a slit pattern here, the wavefronts emanating from the pinhole will be spherical, and the phases that are ultimately produced at the two slits are coherent, that form the intensity pattern that we are familiar with. Removing this pinhole implies that the light falling on either slit will not be correlated, and because it's not correlated, the phase difference is not constant between the two slits, and that causes a uniform white radiance with the intensity variance that comes from the 1 over r square fall off of intensity. The second part was, could you just, yeah, moving away from the source, what can happen is, I'll just use here, if the slits are far enough away, they can now become close enough such that the spatial coherence of the source, in a sense the coherence length, is large enough to cover both slits. And now that the slits are once again in phase, you can see a faint interference pattern. Speaking about the time plots, if you were to take the intensity time graphs, could you guys show those slides? Yeah. So if we look at the slides, oh crap, I built them wrong. Without interference is part A, and with interference is part B. As we can see, without interference, the two intensity time graphs are not at all correlated. They're randomly fluctuating with each other. Whereas with interference, they are in phase, although the intensities may differ. So what this implies is that at any point you will see different colors. You will have colored fringes, but you will have fringes only once there is this spatial coherence at the slits.
The labels are wrongly marked, no?
Yeah, they are. That was a mistake. That's a typo. Thank you.
Okay. ठीक है. IIT Delhi, the question will be directed at you now. You can choose from the second and the fourth questions.
Eating campfire.
Can diffuse before evaporating, and D is much lesser than L. Of the two given configurations below, which system will continue to rotate for longer? He now creates 5 different setups, 2 to 6 ribbons each. They are placed such that the pivots form a regular polygon, and the ends of the ribbon are epsilon apart at the closest
assume that stable means more long-lived, less transient type of machine.
Do we assume any friction of energy losses from the walls of the container?
Don't worry about the walls of the container in this part.
So like if it rotates once, that energy remains in the water, or like there is energy losses.
What do you mean energy?
So this bar moves one up. So now it's also rotating.
Yes, you have to
So the water keeps on rotating.
Yes. And you also have to consider viscous draft due to that is mentioned.
It's not mentioned in there.
Yeah, they didn't tell you to ignore viscosity.
Yeah, they do.
Water does have viscosity. And you have to consider the motion of water in use if there is a
There's a timer.
You have 7 minutes remaining.
there's still like this like between two sides as well. So it's not like there's a gap between two sides. All the volumes, just like the So there are phenomena here that therefore just check if there's something that happens and the global vortex is very slow, and check what happens if it's very fast. We don't want to quantify them because we don't want a quantitative answer, but we would like you to figure out qualitatively what happens differently in both cases, if there is anything different. Also, vortex is moving all around and that's a constant angular velocity. Just assume that it's a global thing. It is quoted. So essentially you have to figure out how to just like this. So if you enumerate the number of long-lived, non-transient long-lived less transient. Long-lived less transient.
You have 5 minutes remaining.
मूविंग इज स्टेबल जैसे जो ज़्यादा मूव करेगा वो स्टेबल है
अच्छा अच्छा
हाँ ऐसा ये सेकंड वाला करेक्ट
अभी जो ज़्यादा मूव कर रहा है वो स्टेबल है बोल रहा है
नहीं उसका अलग है क्वेश्चन
अच्छा ठीक है दे दूँगा
पहले क्वेश्चन नहीं सेकंड वाला ओके
सो टेक माइक
So the first configuration, A would continue to rotate for longer, and the reason is that in the second configuration,
So the strip would move something like this, and the water particles So the water particles in the second configuration would collide in this small region, and so there would be more of an energy loss as compared to the first case. So more energy would be lost in the second configuration. That's why the first one, in which both the strips are going to rotate in the same direction, is going to rotate for longer.
So like I explained for question 2, similar logic we use for question 3. So we consider a configuration to be unstable if for any two consecutive sides it is possible that they both go on rotating without any collision of water molecules in the small area. Like we consider the collision of water molecules to be the force that is stopping the further rotation of the two strips that are in the consecutive direction. So for water molecules to collide for each pair of sides, we get that the orientation of the water repelling and water attracting side must be same with respect to the pivot. So in this case, the water attracting part is this, and similar to this strip, the water attracting part is this. So this would rotate in this direction, and this would rotate in this direction. So water molecules will collide when here water molecules will collide because of the like
2 minutes
opposing rotation. And similarly, if we fix the orientation here, the orientation of this strip also gets fixed. So for any number of sides, there are only two stable configurations.
Yeah, and also for the first part, as we already said that and normally there is an air bubble with the material present, so that's why those air bubbles will slowly dissipate and cause a force for it to rotate.
So by the way, in part 3, all sides from n equal to 2 to 6 would have only two stable configurations.
When there is no global vortex, it will be just like part 3, and the stable solutions are the ones which will rotate the most. When there's a slow global vortex, when there's a strong global vortex, then the angular velocity of water will dominate over the forces of water and Nishadite. So the whole configuration will start rotating with that angular velocity. And when there's a slow global vortex, the rotation of the strips will be slower than the first part.
Okay. IIT Kanpur, you can present now.
So firstly, for the first part, for the first part, as we can see, there will be forces acting at some distance from the pivot. So all of these torques will add up, which will cause the strip to rotate. So that's just for the first part. Now for the second part, what happens is, as the strips are rotating, the water molecules that are close to the edges, they also actually try to move on the direction of rotation. In the first case, the water molecules will actually move in the same direction, thereby reducing the number of collisions and the energy losses, which will allow them to rotate for longer. Whereas in the second case, the water molecules will be moving in the opposite directions because of the orientation, because of the opposite sense in rotation. So this will cause them to rotate for a shorter period of time because there will be more amount of energy loss.
Here there will be collisions. 1 minute.
Here there will be collisions. Here there are no collisions. So okay. So moving on to the third part. So for a stable configuration, we need it to rotate for as long as possible. So for that case, we need to have a stable kind of interaction, like the case here, at all the possible this ones. So at say in this particular region, all of these regions you need to have water molecules moving in the same direction. So this will only be possible for two particular cases. That is one and then the inverting at each location. So for the fourth part, when we have a strong global vortex, these small forces of attraction will not play any role. So therefore, any configuration will be stable. And then when the angular velocity will be the velocity of the vortex. When there is no global vortex, it will be similar to part 3. When there is a slow global vortex, in that case, it will actually, depending on, it will be a mix of both, I would say. So that's pretty much it.
Okay, your time is up. IISc Bangalore.
So basically what happening here is this side is the hydrophobic side. So here what happening is this is the water molecules are doing a elastic collision and they are rebounding back. But here the water molecules are just going and attaching over here because this is hydrophilic. And so there is a net torque due to the, there is a net chemical potential gradient which creates a torque and this guy rotates. Now here what happens is, when the both things are in the both sides, this is more stable because here the diffusion happens like this, but here the diffusion happens in this way, which creates a block to the water molecules here. So
I see your time is up now. IIT Bombay.
So for the first question, since this layer is hydrophobic, it will repel the water and it will rotate in this direction. But because the material is also diffusing and it is vaporizing, so the force which is repelling it will decrease, and then eventually it will attain an equilibrium and it will stop rotating at a particular distance.
In the second question, the A part will rotate for longer because in the B part, both of them are throwing in water at the same location, so there will be energy losses due to collision, and so A part will rotate for longer. In the C part, we are modeling each strip as 0 or 1, 0 showing that it is colored on the outside, 1 showing that it is colored on the inside. There will be only two possible stable states where either all of them are 0 or all of them are 1. In the fourth part, there will be no global vortex. If it is alternatively 0, 1, there will be a slow global vortex if all of them are 1, and there will be a strong global vortex if all of them are 0. All of them are 0 meaning all of the ribbons are colored inside.
Your time is up. Yeah. Okay, judges, you can cross question the finalists if you like to.
You sort of said that because of collision with water molecules, one of those things is more stable. But I didn't understand. Collision with water molecules of what? Water molecules keep colliding all the time. There are 10 to the power 12, 14 collisions per second.
So when the rod, when it is rotating, so the nearby water molecules start moving with that. So the collisions we're talking about are within the water molecules that are moving along with one strip and the other strip, not between the strip and the water.
Okay. Okay,
So
all right.
if we look at the system as a whole, more energy is being lost in the B.
This part is good. In this part 3, you have drawn this picture with 3 strips, and they they can collide with each other, the strips, or is that not possible?
What?
If the strips keep on rotating, will they collide with each other or not?
Yeah, I also thought that, but I assume that some of the strips aren't colliding and they are just rotating like the n equal to 2 case.
I think that is how the question was phrased, but the picture shows they would collide, and if you make them much bigger separation, then they will not do that.
Yes, so
since it was mentioned that D is much lesser than L, which is the distance they would move, so we can assume that.
So that is the distance when they are in the same direction or some such thing. Anyway, go ahead. The next one. So what was this formula you wrote, D equal to mv over something? Can you explain that one?
Sir, can you repeat the question?
I'm asking you to explain what are those equations you wrote at the bottom, D equal to mv divided by something and so on.
Yeah, so in that one I'm trying to find the answer for the first one, like about how the strip will move. So I use the fact that like the element is vaporizing, so like I assume that it's losing mass in a constant, like with a constant rate. So that's like my
Okay, I have no other questions.
Okay, I request the question maker to present the solution.
Maybe I want to ask something from IIT Bombay.
Okay.
So you said that there are two stable configurations for n equals to 3, 0, 0, 0 and 0, 0, 1.
Yes. I made the ... because I wasn't able to write.
I see. So there are how many? 6?
No, there are 8 total configurations. This doesn't represent the stable configurations.
I see. So how many of them would be stable?
Stable will be 2 in all cases, where all zeros or all ones.
All zeros or all ones. So there will be no collisions when n equals to 3, for example, between the...
No, there is no possibility of a collision because the distance between each hinge is 2L plus epsilon. So there is always going to be that epsilon gap between two strings.
Okay, the question maker can present the solution now.
Just give me 2 minutes, I need to erase and then I'll present. Can you click on? Okay. Yeah. So in the first paragraph of the question, we established that if one was to paint a colloidal particle with the material and this direction, it moves in the opposite direction because of this propulsion mechanism. It needs to rotate because it's hinged here and it's confined to move on the surface. So the next question was about 2 different configurations of the painting. And the following. Right. So in this case, this strip would move this way, and this strip would move this way. So if you look at the directions of the angular momenta, this is rotating in one sense, and this is moving in the opposite sense. So this is going to create a net current of water, and there won't be any viscous dissipation because 2 currents hit each other. In the original, just before the water currents are set up, there is going to be a leakage of camphor here. So the camphor that is leaked from this one reinforces this strip's motion, and the camphor that's leaked from here reinforces this strip's motion. Once the camphor evaporates, the vortices that are set up will still sustain their motion, and this will be a stable configuration. On the other hand, here, the camphor that leaks here pushes this strip down, but the camphor that leaks here pushes it up. So there's going to be 2 competing mechanisms here. And even if the vortices are set up, the water vortices move in this direction, there's going to be viscous dissipation. So we would expect this to be more transient and this to be more long-lived. So when you have 3 strips, the lesson we take from here is that these nearest neighbor strips must be rotating in opposite senses. So if this is rotating clockwise, this needs to rotate anti-clockwise. So it doesn't matter whether it's clockwise or anti-clockwise, both configurations are stable. But once this one's configuration is fixed, this one automatically needs to rotate in the opposite sense. So there are two possible configurations here. But here, if we fix the rotational direction of this as clockwise, for instance, this must be anti-clockwise. But if this is clockwise or anti-clockwise, it's going to oppose one of these. So there is no clear winner here. Like there are 6 different configurations where which are equally long-lived, and then there are 2 configurations where they all move in the same sense, and they're all going to kill each other's motion, and those 2 are unstable. This is analogous to a phenomenon in condensed matter called geometric frustration, or rather frustrated magnetism. But the analogy is not necessary here, and it's not very important. In the case of 4 ribbons, it's possible to have alternating patterns, and therefore there are only 2 stable configurations, because you can fix the configuration of the first one in 2 ways, and the other ones are all fixed by that one. They need to all be rotating alternate to each other, nearest neighbors. In the case of 5, there are 10 configurations, and this can be seen as follows. So if we fix this as clockwise or counterclockwise, this is going to move clockwise, this will move in the opposite, this will move in the opposite, and then these 2 are going to have the frustration. And this one could be fixed in 2 ways, and it could be rotated 5 ways. So there are totally 10 possible configurations. When we move to 6, once more we have a possibility for alternating clockwise and counterclockwise rotation, and there are 2 possible ways to do this, because any one ribbon can be chosen to spin clockwise or counterclockwise, and the other ones all follow in the opposite alternating pattern. So the idea of a global vortex was introduced to penalize, or rather destabilize one particular direction of motion. If there is a global vortex that rotates in the counterclockwise direction, then counterclockwise rotating ribbons are going to be stabilized, whereas clockwise rotating ribbons are going to be destabilized. So originally there was a 2-fold symmetry between the clockwise and counterclockwise rotation directions, but because of the global vortex, one of these will be destabilized. So can you move to the last? Oh, this is the last part, okay. Yeah, in the case with no global vortex, what we just said works. When there is a mild global vortex, we need to consider, in any case, we have to consider the interplay of these interactions between nearest neighbors and the global vortex. So if the interactions dominate, then we would expect the usual analysis that we did to work. But if there's a very strong global vortex, then it's going to make all of the ribbons move in the same direction as that vortex. So previously we predicted that in some cases there would be an alternating pattern, and in some cases there would be this kind of frustrated pattern, which leads to a higher number of long-lived configurations. All of this analysis goes away, and everything just circles in the same direction as the global vortex, because that dominates when it's very strong. Yeah.
So, IIT Kanpur, we are left with no choice. Metallic spheres are placed between 2 horizontal conducting plates. Radius is much smaller than the plate separation. We apply an electric field of strength E between the plates. If E is greater than E naught, the spheres pick up enough charge to oppose gravity and start moving between the plates. This is the gas-like phase. If E is less than E naught, spheres remain at the bottom plate. This is the precipitated phase. To make things interesting, we fill the region between the plates with ethanol, which is a low viscosity ionizable liquid, and repeat the experiment. It is observed that the cutoff electric field depends on the direction of the electric field. If the field points upwards and E is less than E naught plus, we observe the pattern shown in figure 1a. If the field points downward and E is less than E naught minus, we observe that the pattern shown in figure 1b. Also note that E naught plus is less than E naught, which is less than E naught minus. Your questions are: first, why is there a dependence on the direction of electric field after the addition of ethanol? Second, give a mechanism for the formation of the 2 precipitated phases when E is less than E naught plus or E naught minus when ethanol is added. The assumptions are: ethanol undergoes electrolysis when the voltage is low enough that no gases are formed. Second, the plates can absorb hydrogen ions. Do you have any doubts to clarify? No? Your time starts now.
separate from this thing? कौन सा टीम ने लिखा था क्या? नहीं था. ठीक. We need to क्या? It would be nice if we can, but अगर नहीं किया तो I said ठीक है. I didn't realize that you would need to do that. Even I didn't know. If the first question के बाद बोले कि ऐसे करो.
You have 7 minutes remaining.
Can I get it? Right. So, இது வந்து without the case button. Yeah. Yeah. So, okay. Cool. We'll have you. So, in our first case, I'm going to give the answer now. So in our first case, as in the very initial case, your field needs to be greater than a certain magnitude for your spheres to attain gas-like behavior. So let's say we are putting adding ethanol in between, and let's say the field first apply the field upwards. So the variable field is upwards, and therefore you naturally have ion accumulation, positive ion accumulation in the upper surface and negative ion in the lower surface, and this will cause a net, let's just say, repulsive force downwards due to the accumulation of ions, and therefore the net repulsive force has now increased, which was initially g earlier. Therefore the variable force needs to be greater than this particular value, which is in this case upwards, I guess, right? So E naught plus. And for the second case, you basically have the accumulation of ions opposite to the previous case. So you will have positive downwards and the negative on the upper surface. So your ionization field is now opposite to the previous case, and therefore you will have a net decrease in the repulsive force. And therefore your variable field needs to be greater than a lesser magnitude, which is E naught minus. So E naught plus would be greater than E naught minus. That's the summary of the first part, and then working on the second. No, yeah, working on the second. We're working on the second. Yeah.
You have 4 minutes remaining. You have 2 minutes remaining.
Okay, so for the second part, so what happens in A is, in A, the plate where the deposition is observed, so there are H plus ions that move towards this direction because of the field. So these H plus ions are absorbed. So as a result, we see a sort of a uniform kind of distribution of the metal spheres. Whereas in the second case, it is the ethoxide ions, C2H5O minus ions, that are deposited on the plates. So this causes the metallic spheres to, arrange themselves in a non-uniform way, which results in that particular pattern. So that is a rough mechanism that we could think of. So, yeah.
You have 69 seconds remaining.
You have 30 seconds remaining. IT Kanpur, your time's up.
In here, first of all, there is imbalance in the E negative and E positive because of the diffusion of H plus ions onto the negative plate. They'll be diffused onto negative plate. This is the case for the positive upward direction electric field. Here, since the process will start when the EQ is equals to mg for the balls. So in here, the Q charge on the balls will be mostly dependent on the sigma of this field, because negative charge is distributed in the whole liquid in the form of ethanol ions, and the positive charge is on this field. But for the negative direction, the positive charges are on this field, this plate. So potential on this potential at these points will be lesser. So the charge on the sphere acquired, which is kq by r, would be lesser, so Q is lesser. So basically that's why there is difference in the two electric fields. Now when the spheres are falling, they'll try to push the H plus ions, and due to the push of the push of the H plus ions, there will be some regions created where the H plus ions are in less concentration than the other regions. So all the subsequent spheres will try to go to that region only, and that's why we see the pockets of different concentration for this case. But while in this case, since there are no H plus ions on the bottom bottom plate, they'll more or less fall uniformly, and hence we get the patterns we observe. Yeah, so that's the mostly what we want to say. Thank you.
Okay, so first of all, ethanol will dissociate.
You can't start. Wait. You need to wait for your timer to start.
Yeah, so ethanol will first of all dissociate into the anion and cation. In the first case, when the electric field is upwards, then hydrogen ions will move towards the top plate and the anions will move towards the bottom plate. In the second case, it will be opposite. In the first case, the induced electric field will be higher, and in the second case, the induced electric field is lower. Therefore, to move the balls, it will be easier in the first case, and that's why E0 plus is lower than E0 minus.
For the last part, the C2H5O minus is near the bottom layer, and the charges in the sphere are also in the same manner. So both of these repel, and since C2H5O minus is not absorbed in the lower plate, they both are free to move. Hence, they equilibrate at a point where they are at maximum distance. So we can see a uniform equilibrium. Whereas in the
Time's up.
B
Time's
part,
up. I did tell you your time has started.
Yeah, so our reasoning is roughly similar. When the electric field is downwards, hydrogen will go down and be absorbed on the plate. And when it is absorbed, there will be regions where there are more hydrogen, and as such we'll get the pattern that we find in B due to the repulsion between the metallic balls and the hydrogen that is dissipated, that is absorbed by the plate. And when the electric field is up, then the ethanol ion will go down instead of H plus, and it is free to move, and it will distribute itself uniformly, and we'll get the pattern that we find in A. And as for the reason for the difference in their cutoff electric field, it is because of gravity, and that when electric field is downward, H plus will have to go down, while ethanol ions will have to go upwards, which is against gravity. And that's why E0 minus is greater than E0 plus.
Your time's up. Thank you. Now to the judges, do you have any questions?
So I had one question for IITK. So these metallic particles, what is the charge on them in the case when the electric field is up or electric field is down?
When the electric field is up, the charge on the metallic particles will not be anything because the H plus particles will be on the top plate. Whereas when the electric field is down, the H plus particles will be on the bottom plate, giving the bottom plate some charge, which will be acquired by the metallic spheres when they precipitate. So, in the second case, they will have some charge.
My question is also from your team. So on the board you wrote E0 plus is larger than E0 minus. So are you contradicting with the experiment?
Mix the cases up.
Sorry?
No, mix the cases up. So it's supposed to be.
So it was a typo error?
Yeah.
Okay, typo error. Thanks.
Now I call upon. No more questions, right? I call upon the question maker to present the solution.
your medium just has a bulk negative charge. The H plus ions are sort of just removed from the medium. So they really don't have any part to play in the mechanism that explains the two phases that form. So first let's, okay, so everyone seems to have understood the fact that there's an electric field that either opposes or supports the externally applied electric field in the upward or downward cases that results in the cutoff values changing. So that part I really won't go into. So the mechanism of the formation of those two phases. First let's consider the case where the electric field points upward. So here your spheres will acquire a positive charge since they're resting on the bottom plate and the bottom plate is positively charged. And your medium has a bulk negative charge. So since any given sphere or any small precipitate of spheres has a positive charge, if there'll be a local region near these spheres where the charge density of the bulk is higher. So you'll have a local region around a positively charged sphere where this negative charge density is higher, and as a result you'll have this negatively charged region move down at a faster rate in this external electric field than the surrounding negative charges, and those negative charges will rush into the void created by the movement of this region to create a sort of vortex of negative charges. Yeah, in the case of an upward electric field, this moves downwards, and a vortex of vortices of vortices like, wait, this are created, and yeah, that results in these spheres moving apart from each other and forming the first pattern that you see over there. Yeah. So similar explanation for the second case where you have vortices of the opposite sense but created by these regions of higher negative charge density moving upward, and that results in your spheres moving okay, so here you have a higher negative charge density in a region that's close to one sphere since the sphere is positively charged, but there you'll have a higher negative charge density in the region between two negatively charged spheres since negative charges repel. So that leads to vortices that push negatively charged spheres together. That leads to the honeycomb pattern that you see in the second case.
Sadly, this is where Physics Deep Thought ends. Hope you all enjoyed the questions and answers. I call upon Mimamsa GC Dipansh now.
Thank you everyone for being present here. I want to thank you judges for being present here. There are refreshment for all of you. It's outside the this NLH, so please have it. I request team coordinators to be with your team. We will be having ECS Deep Thought after half an hour, so it will start at 5. So be here on time.